Hi students, and let's discuss another important concept in wave mechanical model of the atom is applications of Schrodinger wave equations. So in your previous class, we have discussed regarding the wave functions, how that wave functions plays a vital role in finding the particles associated with what waves. When the particles exhibits in a wave nature, that wave should have an what a certain equations. So that equation was derived by our scientist using Schrodinger. Okay, so let us see how that Schrodinger time independent wave equation is used to what find the particles in a one-dimensional box. Okay, so now, so for that, consider what is a particle confined to a box of length L with infinitely high walls. That means the box is that particle is what existing. The free particle is existing in a box of length what L with the what infinite walls. So the particle is what recoiled back and forth elastically. So as shown in your what figure it is. Okay. So here now let us put the certain condition for the motion of this particle. So what are those? The first one is the particle should move. The particle moves alongwards x-axis between x is equal to 0 and what? X is equal towards L is. Okay. And since the recoil is elastic, it does not lose energy during what is a collision, so that the total energy remains in what is a constant. The total energy remains what is a constant during its what motion. The second condition for the motion of the particles inside this box is the particle is free particle. That means it is not subjected to any external force. The potential energy is taken to be what? Zero inside the box. What is the potential energy is taken to be zero inside the box, so that we could zero for what x lies between what 0 to a L. Okay, 0 is less than x is less than what L. That means x is lies between what 0 and L. In such case, the value of E what E equals to 0x. Okay. The second one, whatever that I will tell. Next, the value of the what wave function is 0. Whatever that value of the what wave function is 0 for what x is less than or equal to 0 and x is greater than or equal to what L. That means it means that the value of the wave function is 0 outside the box. And one more thing, the potential energy of that particles outside the box, the potential energy outside the box is what is okay. The potential energy outside the box is taken to be what is whereas the wave function of the particle outside the box is what is 0x. Okay, so these are the conditions for the motion of the particles in a what one-dimensional box. Okay, now so let us write the equations for time independent wave equations for one dimensions. Those cosine by dou x square plus of what 8 pi square m into what capital E minus of v into bracket close that bracket sine divided what x square towards 0. So here in the above conditions, what we made is the potential energy of the particles. So inside the box is what is 0. Okay. So on putting these conditions, so this becomes what? Dou square sine dou square. This is dou x square. So this becomes t square. So we make it correct. This dou square sine divided by what? Dou x square plus of what is k square into sine 0. Where k is a constant, the value of k square is equal to 8 pi square into e divided by what is x square. Okay. So here after this one, the general solution of the above equations The general solution of the above equations is given by sine is equals to a cos 2x plus b sine 2x, where a and b are what? A constants to be determined. Okay. So by using applying a boundary conditions to this your equations too, so we can calculate what the value of a and b. Let us apply the boundary conditions. If x is equals to 0, if x is equals to 0, the value of your what? The value of your what is the value of if x equals to 0, psi is equals to what is 0. The value of your wave functions outside the box is taken to be what? 0. That means x lies between 0 and what is what? When that your wave function, the wave function of that particle is taken to be what? 0 outside the box. That means when x is equal to 0, that your what? Psi becomes what is 0h. When that x is equal to 0, the psi equals to what is 0h. So that your above equations becomes what? 0 equals to a cos 0, because you are substituting x equals 0 instead of l. That's why it becomes cos 0 plus of what? B sine 0x. So it becomes what? A equals to, so cos 0 is 1. So you are getting what? A equals to, again you want to apply that your boundary condition. What is the value of your wave function at x is equals to L? Again at x is equals to L, the psi is 0 because the wave function is having certain values, single values inside the box. When x becomes L, then it becomes what? Outside the box. So that your psi, again the psi equals to 0, the 0 is equal to b sine k, because the value of your a is 0, so that you are substituting here. Your above equation becomes what? 0 equals to b sine k. Okay, the k is equals to what? Root of 8 pi square ne divided by x square. Okay, but p is not equals to what it is 0. So that value of these three words that we combine. Next, after this one, so see here, that's also written here. B is not equal to 0 and sine kl equals to 1 0. So this that is sine of k is this much 8 pi square me by x square into l equals 0. So this equation is true when kl is equals to what? N pi, where n is equals to 1, 2, 3, and so on. Okay, allowed quantum number is where the root is nothing but what? K. The k into l is equals to n pi, or k is equals to what? N pi by what is l is there. Okay, so make its classifications or make it square on both sides. So you get it what? 8 pi square m e n l square by n square into 1 n square pi. Okay, so pi square get cancels. Then you have to write that e n. The energy of the particles in the nth state is given by E of n equals to n square, h squared is what? Mn square. So this equations so gives the allowed values of energy for different values of n. I'm substituting n is equals to 1, so that you are getting what? The energy of the particles in the first state. That state we are calling what? Ground state. Thus the particle has the value of what? Energy. The integer n is called as quantum number. So whatever that particle is there, that's having what? Fixed values, or you can call it a discrete value of energy is there. Okay, so each particle is having a what? Definite amount of energy in what each. Okay, so for what? Allowed each values of your quantum number. Okay, suppose if you substitute n is equals to 1, so you are getting what? H square by what? 8 ml square. When you substitute n is equals to what? 4h square divided by 8 ml square. Like this, you are getting what? All the values in your different states. So these are called as what? Eigenvalues of what? Energy. So this equation we are calling it as what? Eigenvalue, the expression for eigenvalue of energy in the nth state is given by n square h square equal to what? 8 ml square. For the first state, we are getting what? H square bar 8 ml square. 4h square with second state means first excited state divided what? 8 ml square. Like that, you are getting what? And a different amount of energy in what different states corresponding to the what? Allowed value of quantum numbers. So these are called as what? Eigenvalues of energy. The energy corresponding to what? N is equal to 1 is called what? Ground state energy. The other energies, we are calling it as what? Exact states. Okay. Next, in the above case, so we need to calculate what the value of B, but the value of A is 0 in your general equations. By using your boundary conditions, so you have determined the value of what is A. Next, so the value of B is not equal to what is 0, but that's having what certain bars. So you consider the equations. When you consider that psi is equals to A cos kx, that A is 0, that's you want to leave it a0 means psi equals to what? B sine kx. This is what? B sine kx. Or you can write what? KL. B sine KL. Okay. This is K. Or you can, this one is what? K. But in the above case, so here you are getting what? This is root of this one. This is nothing but K into L is equals to N pi. So therefore K is equals to getting what? N pi by L is. The same thing what we insert here. Okay. Psi is equals to B sine of is what? K is K. This is K. The value of K is what? N pi by L into what is X. Okay. Since the particle is inside the box. Okay. So you are what? Finding the particles inside the box. So that the particle is when the particle is inside the box, the probability of finding the particle is what it is 1. The probability of what? Finding the particle is what? A unity. So by using your normalization conditions, the integration for the entire space. The entire space is means so that's your what? Only one dimensional box is there. That's why this is taken as what? Integration of 0 to L, the model of your what? A size. The square of the magnitude of your wave function to dx is equal to what? 1. Now let us see what substitute this value inside the what in the above equation. So it becomes what? The integration of 0 to L d square sine square n phi into x by what L, because n phi by L is nothing but your what? K is there. That value I have what? I inserted here. So in the above itself I have what insert into dx is equal to what is that. But this one you can put it like this. So d square by 2 into 2 sine square n phi 2 sine square is what is n phi into x is what x y is what is L is 2 sine square n phi x y is what L into dx. That is equal to what is 1. This one you can put the in your mathematics. So we are having a formula. The 2 sine square n pi x by L is nothing but what? So 1 minus cos of what is cos of is what? N pi x divided by what? L is. So into is what? Dx is equals to 1. So you want to what? Integrate separately d square by 2 into integration of 0 to L 1 dx minus of integration of 0 to L cos of what is n pi x by L into dx is equal to what is now 1. Okay. So here the integration of that second term becomes what is 0. So that's right. Integration of one is x d square by 2 x between the limit what 0 to what is L. Now we have to put the limit upper limit first. B square by 2 into what is L is there. So we need an equals to what is 1. We require the value of what is B, so that the value of B equals what root of 2 by what L. So hence the eigen functions, that's your equation psi is equals to, we are having what B sine of what is n pi by L into x is there. So I'm substituting the value of your x for it is k. You are getting what? N pi by what? L. So that your above equations becomes what? The wave function of the particles in the nth state in a one-dimensional box is given by sine of x is equal to root of 2 by what? L into what? Sine of n pi by L into x. So this is general equations, so which indicates the wave function of the particle in a what? A nth state for a one-dimensional box. Okay. Suppose if you substitute n is equal to 1, so we're getting sine of 1 is equal to root of 2 by L, sine of pi by L into what is divided x. So that for psi 2 equals what root of 2 by L into what is sine of 2 pi by L into x. So just go and get it. You will get it when you are substituting the value of n is equal to 1, 2, 3 and so on. So these wave functions are what? Identical or say with the allowed amplitude functions for a standing wave in case of what is string fixed state of what is about n's. Okay, so like this, so we are determining the energy of that particles in a one-dimensional box. So we have derived equations E of n is equals to n square h square divided by 8ml square. And at the same time, so we have derived the wave function of that particles. So what role that wave function plays in finding the particles, that's already I have told it is that wave function of the particles is given by psi of nx is equals to what? Root of 2 by L into sine of what is L pi by L into x. Okay. So this is the what? In this way, so we are using our Schrodinger time independent wave equations in case of what? One-dimensional boxes. Okay. So we will discuss the next concept of the linear harmonic oscillators in the next session. Thank you.